Hi everyone, let's work on some examples that actually make us use the second part of the fundamental theorem of calculus. Sorry, my voice is extra rough this morning. So I would just say that really the big deal with the second fundamental theorem is it allows us to construct an antiderivative of anything. So right now we have a very limited set of functions that we can actually find an antiderivative for. In chapter 2 we're going to be learning some techniques for working on more complicated things. But the truth is that even when we're all done, there's going to be a way longer list of things that we cannot find a nice easy antiderivative for than things we can. So the second fundamental theorem sometimes gets called the construction theorem because that's what it allows. It allows us to easily construct antiderivatives. They're not nice antiderivatives, they involve integrals, but they at least give us a formula that we could get numerical values of the antiderivative. We could use that to get a pretty good sketch of the antiderivative. So while not ideal, they are antiderivatives and we can work with them. Okay, so for example, if we're looking at the function big F prime right here, this is not something that I can easily just find an antiderivative for. This is a composition of an exponential and a cubic function, so we would get pretty stuck in a hurry. The second part of the fundamental theorem tells us that if we build an area function, and we can start wherever we want, so let's just do this for now. If we build any old area function, so you pick the bottom limit, the top limit should be your variable. Oh, and I'm being not careful right now, but that's okay because I wanted to make a big deal about this. Because I have chosen the variable for big F to be x, that means that variable inside the integral has to be something else. Doesn't really matter what, as long as it's not the same thing. We need one variable that allows this to actually be a function and take on different values. And we need a separate value here so that we're not saying, oh, here's actually a really good example. If we set it up like this, 0 to x, 5 to the negative x cubed plus 2 dx. So this is a side note, this is bad. And then we wanted to find f of 2. We'd get the integral from 0 to 2 of 5 to the, negative 8 plus 2, 5 to the negative 6 d2. And here is a really good sign that something is not going right. How can the width of our rectangles be an infinitely small change in 2? That doesn't really work for me. So just make sure you do have two separate variables or it's not going to make any sense. So this is an antiderivative. It's a perfectly good one. If all I was asked was write a formula for the antiderivative, I could quit. But I actually have some specific info here, and the point of this problem is just to force you to practice with this building antiderivative stuff and recognizing that that's what this is. So recognizing this as an antiderivative, number one thing here. So if I want to make sure this thing goes through 2, 4, I could start by plugging in 2. So let's see. Because I don't want, let me say it this way, because I don't want just any antiderivative, I'm going to put the plus c on here and say I have to find the plus c. If I wanted any old antiderivative, I could just make that plus c 0 and I would be great. So if I want to do this, I know that that should equal 4 because I'm told that f of 2 equals 4. The trouble is that the whole reason I'm doing this is because I can't nicely just write down a formula for the antiderivative of 5 to the negative t cubed plus 2. So you could use technology at this point. Oh, sorry, yawns. Bad voice and yawns. And that would give you a number to replace that integral with, and then you could get an approximate value of c. But let me actually erase this and go back to where I started and show you an easier way. So I want you to be really clear on the fact that that would be fine. You could build it that way. Totally okay. But if we know that we want our antiderivative function to go through 2, 4, another way to mess with I guess that can stay there for a second. To mess with the vertical shift on an antiderivative that's built this way is to adjust this. So now it makes it really easy to figure out what f of 2 is. So that's kind of the goal. And again, the deal is that this bottom limit can be anything you want it to be. It doesn't matter. It's just going to mess with the, it's going to change the plus c basically. It's just going to shift your graph. And we can either just say we don't care what our plus c is, or we can adjust it to match that. So if we build this way, knowing that 2 is a value we have some information about, we're going to get this. And that is actually easy to figure out. So this integral is 0, which means our plus c is 4, which means I can go back up to this top formula and say there is a formula for not just any antiderivative, but the specific antiderivative that goes through 2, 4. Okay, so if that made sense, pause, work through the next couple, 3 of these, and then check back in. So here we have function little g of t. We want to find a formula for big G of t, knowing that g of negative 3 is 107, and g prime is equal to little g. So this is another one we're just looking at that square root of 1 plus t squared. That doesn't immediately look like something I know what to do with. So I am going to say my big G is going to be the integral from 0 to t of the square root of 1 plus, and here's where the variable changes. I'm being kind of deliberate about this. This asks for a g of t, so I know I want this variable to end up being t, which means it's this inner variable that has to change. Okay, so there's a starting point. I'm going to mess with this again. This is an antiderivative of g, little g. When I put the plus c on, it becomes the antiderivative. It's this general categorization. This would capture all antiderivatives. Just change your plus c, you'll get a different antiderivative. I can also adjust my starting point, and I think I'm going to, because if I want it to be easy for me to write down a plus c on this, it needs to be easy for me to calculate g of negative 3. So now I can say g of negative 3 is the integral from negative 3 to 3 of the square root of 1 plus x squared dx, which is going to be 0. And I want that to end up being 107, which means c has to equal 107. So that's my answer right here. Okay, for h prime equals e to the sine z, we want h of pi to equal root 51. Okay, so we want the antiderivative. And since we know we want to mess with pi, I'll just start with that this time. Pi e to the sine z. Oh, hold on, I can't use z. X dx plus c. Okay, so there's the whole family of antiderivatives. We know that when we plug in pi, we're going to get the integral from pi to pi, which is 0, plus c, and that's supposed to equal root 51. So our root 51 is going to be our c. So again, if you carefully choose that lower limit, it makes the plus c really easy for this type of function. Doesn't mean you can't choose anything you want for the lower limit, it just means you'll probably end up having to use technology, and you'll only have an approximate c value, not an exact one. Okay, last one on my list, j of w is tangent w. I want to find its antiderivative given that j of 11 is supposed to equal negative 42.3. So j of w, we're going to integrate from 11 to x, tangent x, And plus c. So there is the full family of antiderivatives. We know that when we plug in 11, we get 0 out of that integral. What we want to end up with is negative 42.3. Okay, so again, I want you to be really clear. It's not a general rule that given a point, you just make the y-coordinate your plus c. That only works because of the way I'm building this antiderivative with 11 as my lower limit. Okay, so that's how we construct an antiderivative. I want to say again, this is not ideal. If you ever come across something that you can just find the antiderivative for, a nice formula for the antiderivative, do it. This is only a tool for when we can't do that. I'm thinking right now that I forgot one part of this first one, and it's nothing too crazy, but just to make sure you're clear on how these functions work, if we actually wanted to, I'm just going to do f of 1, use one of these functions to find a value of the antiderivative, it does become, again, a technology question. But that is better than the nothing at all that we had before. So before this theorem, I wouldn't even be able to write down any way to find values of big F. I now have this formula that tells me how to find values of big F. I do need technology to use that formula, but at least I have a formula. Okay, so I think that's it for number 6. Thanks for watching.